Welcome to lecture 1.2. So what I want to do is I want to talk a little bit about the mathematics of Legos. And before getting into something as complicated as Legos, I thought I would start with something a little bit easier. I actually have many jobs. In addition to being a math professor at Williams, I'm also a tic-tac-toe hustler. So I play at the Williamstown Elementary School, mostly over the summer. I don't want to play outside in the cold. These are outdoor games. I have never been defeated by an elementary school kid in Williamstown. I have been tied once, though, but for the most part, I'm going to share my tic-tac-toe secrets. Now, for those of you who haven't played tic-tac-toe, the goal is to get 3 X's or 3 O's if you happen to be O's, which I don't know why you'd want to be, in a row. It can either be horizontally, vertically, or diagonally. All right, so a tic-tac-toe board looks like this. This is about the level of my artistic talent, which is good. How many opening moves are there in tic-tac-toe? Give me the answer I want. No. No. Wow, I've heard 3, 1, 4. Not quite sure where 4 is coming from. 9. Let's go with the simplest. And I actually did this in my daughter's kindergarten class. It was hard getting them to just count up to 9. All right. 9 is an obvious first answer. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you just look at the game naively, there are 9 opening moves. All right. But now I hear someone saying, this is my soccer guy. Yes. And so how many opening moves are there? There's 3. The corners are all equivalent. So if I move over here, this is the same as moving over here. One thing is to bend down like this. Another thing is to pick up the board and rotate the board. If I draw an X here, if I rotate the board 90 degrees like that, that's the same as the X being here. If you don't want to rotate the board, instead of rotating the board, you can rotate yourself. Any physics majors here? Any math majors? This is essentially the difference in linear algebra done by the physicists and linear algebra done by the mathematicians. When you write down a 2x2 rotation matrix, are you rotating the coordinate axes or are you rotating the points? And depending on what you do, it's going to be a little difference in terms of where you put the minus sign. Hopefully you all understand that the 4 corners are the same. All right, building on that wonderful insight, what next? The sides are all the same. And then there is the center. Now, somebody said that there's only one opening move. And why is there only one opening move? I'm sorry? There's only one good one. In some sense, that's wrong, because as long as your opponent plays well, it doesn't matter. It's always going to be a draw. But there's more chances of somebody making a mistake. And so when you're trying to analyze this, why is the center so much better? Excellent. So it kills 1, 2, 3, 4. So in one move, you ought to kill 4 things. So there are 2 ways you could play tic-tac-toe. You could play to win, and you can also play not to lose. And if you're playing not to lose, going here kills 4 things already. Any Star Trek fans? So I taught a class on Star Trek a couple of years ago with Professor Strzok in physics. Next Generation fan, by any chance? Okay. Do you remember the episode where Data is blanking on the game right now, where he's playing the video game against the Zactor? That's exactly in some sense what's going on here. Since there are not that many Star Trek fans, I will not elaborate that point. Stratagema is that sometimes the goal is not to lose. And so here, it's not that hard to analyze tic-tac-toe. Naively, if you try to figure out how many possibilities are there are 9 opening moves. How many responses are there? 8. How many responses? How many responses? How many responses? How many responses? Yes? Sometimes somebody's already won. Excellent. So email me for extra credit for tic-tac-toe knowledge. Right? At this point, the first person has already gone 3 times. Am I in focus with the camera? Okay. So at this point, it is possible you might have the, two moron or one moron playing tic-tac-toe doing a strategy like this. And the game might already be over. So in terms of analyzing how many games there are of tic-tac-toe, this is a non-trivial problem. And here, it all comes down to how do you count. So one of the goals of this class is to show you how very simple problems can have very complicated answers to them, and that the answer can depend on the metric you use. This is very similar to what we were talking about earlier with the different statistics we use. Do we consider this game different than this game? I mean, I can get these games by essentially flipping the board. I can't do it by rotation, but I can do it by flipping, by looking at it in a mirror. I really don't want to consider these two games different. But for counting purposes, it's actually easier if I consider them different. It would also be easier if I allowed the games to continue even after somebody has already won. And say, okay, oh, I know you've lost, keep going. Hey, and O can then feel happy, right? It makes it a lot easier if we consider the games to continue. Any World Series fans, baseball fans? How do you win the World Series? Best of 7. Whoever wins 4 games first wins. If you're winning, 4 games to 1, you're not playing games 6 and 7. You stop. We're not going to say, okay, you've lost the World Series. We're just curious as to how much you would have lost by. We're going to just, no, you stop. But from an analysis perspective, it's often easier to just allow the game to continue. And so a nice challenge is to actually enumerate how many different games there are of tic-tac-toe with or without symmetries. If we do it without symmetries, there's a lot of stuff to analyze. It has been done, and it's a nice calculation to read. That said, I would much rather analyze it with symmetry. And this is how you can get really good at tic-tac-toe. So how many opening moves do I have to really worry about? Without loss of generality, is the opening, does it matter if it's X or O opening? No. So let's assume X starts. So I can have X go here. I can have X go here. I can have X go here. How many responses do I have for O? How many? 5. 1, 2, 3, 4. So there's 5 possibilities here. How many possibilities are there here? Also 5. 1, 2, 3, 4, 5. How many possibilities are there here? 2. So I can go in a corner, or I can go on a side. So I told you you would have, basic algebra prerequisites. This adds up to, whereas 9 times 8 is 72. I hope it was 72 and not 62. So how much do we save? So one way to look at it is we save 60. A better way of looking at it is to say we save a factor of 6. And then when you start to look at the tree as to how many possibilities there are, as you continue, there's a lot fewer cases now to look at in the tree. And so, as a nice exercise, you can continue this and try to look at 3 levels deep. And this is how you can very quickly find optimal strategies in tic-tac-toe. So really, there's only 3 possibilities you have to worry about for your opening move. If you're on offense, it doesn't really matter too much. You can very quickly learn that if you go in the center and somebody responds by going there, you can trap them. So then the question becomes, what is a good way to analyze something like this? In tic-tac-toe, to me, one of the best things is if you attack somebody multiple ways at the same time, they can't defend both of them. So you want to try to attack them in 2 different ways, and then they're in trouble. But how do we do the analysis? There are so many cases. What you can do is you can break things down to, let me get them in a situation where their move is forced. And if their move is forced, the analysis becomes very easy. So Can anybody tell me a good place to go for my next move? There's multiple answers that will work. Yes. Lower left-hand corner. That's one of the wins. If you go here, where does O have to go? Upper right or O loses. So we'll assume O goes here. So you could go middle left. I prefer to go, corner as well. Doesn't matter. Right? You have lots of ways. If you go here, you're attacking this way, you're attacking this way, and the analysis is done. And so you can now prune that entire branch in terms of what is the strategy. Because very quickly you get O into a point where O's move is forced or you win. That's not that much analysis. Now you have to do a little bit more work for the other cases. For the most part, tic-tac-toe is a boring game. Okay? I know a couple of interesting variants of tic-tac-toe. One is to use a larger board and try to get 4 in a row, 5 in a row, 6 in a row. And what you can do is if you do something like this, you can give a little bit of a boost to whoever goes second because they have a disadvantage. Maybe you put a couple of O's already on the board spread out from the center. And if you do something like that, you can come up with a nice handicap to try to make the game a little bit more even. You could play tic-tac-toe on a Taurus. Wrap around. Lots of interesting things you can do. Have you ever seen bidding tic-tac-toe? There are 2 variants of this. You each start off with $1,000 and you bid on the opening move. And whoever bids highest gets the opening move. And in one version, whatever you bid, the winning bid goes to the banker. In the other version, the winning bid goes to the person who bid less. And then you bid on the second move and the third move and the fourth move. Do you want the first move? First move is pretty good. We talked about how it's advantageous to go in the center. How much is the first move worth? I'll give $1,000 for the first move. So this becomes a really interesting question. How much is that move worth? Especially if the other person gets the money. What if you pay $1,000 for the first move? How much will the person... So you get the first move. It's your lucky day. You bid $1,000. The other person bid $15,000. You overpaid. So like the Red Sox have done for many players over the years. Crawford is a great example. Daisuke Matsusaka is another one. So now, player 1, player 2, player 1 has 0, player 2 has $2,000. How much does player 2 bid for the next move? $1. We can argue as to whether or not you can do epsilon and fractions. We'll do $1. Where does player 2 go? Anywhere. How much does player 2 bid for the next? $2. Player 1 is desperate now and bets his entire stash again and is now regretting that huge bid. Player 1 loses $1,997. And now it should be pretty clear. How much do we bid? Oh, we bid $2, right? So this is now $3. So we bet $4, $1,993. Player 1 ends up with $7 and loses. So it's good to get the center, but there's a limit to how much you're willing to pay for that. Which moves do you really want? If you can get moves 3, 4, and 5, that's really good. You can win with moves 3, 4, and 5. You can't block off a winning combination with just the first 2 moves. This becomes a really interesting way to play tic-tac-toe. The other interesting version I know of tic-tac-toe is gobble tic-tac-toe. It's almost like Russian doll tic-tac-toe. Russia is on the offensive again. All right, so you have the 2 big pieces, 2 medium pieces, 2 small pieces. And on your turn, you place down a piece, either on an unoccupied square or on a larger one, you can gobble up something that's already there. And you can gobble up your own pieces. And then the question becomes, how do you play something like this? What is the strategy? All right, so why am I talking about stuff like this? What is the connection of this with Legos? This should hopefully sound like a very simple problem. I have 2 Lego bricks. How many ways can I combine them? Now, the first thing you learn in a math class is the importance of having a problem well posed. Is this a well posed problem? All right, what are some of the questions you might have? Yes? Do they have to be at right angles? If not, I actually have infinitely many possibilities. All right, what else?
Do they have to interlock?
Do they have to interlock? Does this count? Does this count? Can I slide down like that? Yes?
How big are the bricks?
How big are the bricks? And just because I'm holding up these, let's say we're holding up these two. I think the standard problem involves 2x4 bricks.
Are the bricks interchangeable?
Are the bricks interchangeable? Are these bricks interchangeable? They have slightly different colors. I think I can give away one line from the Lego movie. I apologize for those of you who haven't seen it. At one point, Batman is building something to help the good guys. And he says, I need all your black pieces. I only build in black or very dark gray. And so here, these are slightly different colors. If I care about how many different combinations I have, do I care that these are different colors? Probably not, but you have to be clear and you have to specify. I am talking about 2x4, standard bricks, and I don't care about color. The next question I have is, I can consider this, and I can consider this. Are they the same or are they different? Why are they the same? Yes? Symmetry. I can rotate them like this. So in terms of rotating, it's just a matter of how I'm presenting it. All right? So there's lots of very interesting questions you have for something like this. And I believe it's called chirality. Any biologists here? Okay. This is important. If you do this wrong, you can actually kill people. Let's look at 2 tic-tac-toe games again. So first move is go like this. Person responds like this. Second move, and then third move. All right, so it's 3 in a row, game is over. Are these games equivalent? They are equivalent. I can't get, however, from this game to this game just by rotating the board. What do I have to do? Oh, crap, I did it wrong. Did I do it wrong? Oh, wait a minute. No, sorry. They look the same at the end, but the game is actually different. 1, 2, 3, 4, 5, whereas this was 1. Oh, yeah, you're right. Okay, so sorry. We want to do it this way. 1, 2, 3, 4, 5. Okay. Now it's hopefully drawn correctly. All right. So these games are equivalent. And I can get them by flipping this about the middle. It's one thing to pick up a human being, I can do this with my kids, and turn them upside down. To flip their internal organs and everything like that, that's a bit harder, and DCF would probably get on my case for something like that. Are these the same? It depends on your definition. If you look at certain biological compounds, certain chemical compounds, mirror images of compounds have very different chemical properties in terms of how they interact with things. And one thing can kill you while another thing could save you. So it's extremely important when you're doing stuff like this that you decide carefully what you mean. So let's talk a little bit about how we would analyze this. How many ways are there to place the first brick? Find a reference frame, right? Choose it like this, or like it doesn't matter. There's really just one way of placing the first brick. We're going to declare that the only combinations we allow are the combinations where the bricks are interlocking and only right angles are allowed. How many places do I have, or how many ways do I have to add the second brick? So somebody tell me one of the possible paths to do. Yes?
Place them directly on top of each other so that
Like this?
you get one that's twice as tall.
Okay, so one is like this twice as tall. And now the question is tweaking this. So in this way, we have the two bricks with the same orientation. So one of the hardest things in combinatorics and probability is avoiding double counting and being complete in your counting and making sure we don't miss anything. So one possibility is to just go straight down. We have one like this, where it just goes over the very first, and then we start moving it down. Oops. We start moving it down 1 unit at a time. So now we have it like this, where it covers 2 of the 4. Then we move it down again. Then we move it down again. Do I need to move it down again? We already had that when we were up over here. So in terms of how many ways to count it, once we're down here, what we can do is we're allowing ourselves rotations. It rotates up to be the same as this. So how many possibilities were there if we go straight down? 1, 2, 3. There were 4 possibilities. We could also have it offset by 1 on the side like this. How many possibilities are there? So if we go all the way down to this, is that different? So let's see if I have enough Legos to do this. All right, these ones are a little bit thicker, we'll just pretend. So here I started off like this. And in the other one, I started off in the bottom corner over here. Are these the same? They're mirror images. In some sense, they're reflections of each other. If I draw something down the middle and reflect about that line, they're the same. The question becomes, do you consider these the same or different? I don't know about you. I cannot flip Legos. I can rotate Legos. To me, I would consider these different configurations. And so when you look on the Lego sites as to how many combinations do you have, you will get different answers depending on how you classify something like this. However, if you look at this in a mirror, this will then look like this, I believe. And so in terms of structurally, are they the same? There's a very simple mathematical transformation between the two. So when you're trying to count, you really have to be careful. You really have to be clear. This is one of the things I want you to get out of this class, is pose the problem well. And if you know exactly what your definitions are and what you're counting, then hopefully you can all agree upon an answer. If you're not clear, different people will get different answers. All right, so we can now figure out how many ways they're doing it like this. What's the other possibility? Is now we have to worry about doing it like this and going through the different combinations. It's not that bad to do just 2 bricks. As a nice exercise, try to do 3 bricks. There's a website that goes through the detailed calculation of doing 6 bricks. For those of you who want to try your hand at some computer programming, write a computer program to determine when these configurations are equivalent or not, and go through all the different possibilities. This is a really nice challenge to write something to go through and see, is there some kind of moving involving rotations and flippings that makes them equivalent? And again, it doesn't really matter how many ways there are to combine them. The answer is in the millions. What's important is the skill that you get from doing something like this, from being able to do the analysis of this and see what the level of complexity is. Another question you might ask is, what if I use different size bricks? How is that going to change things? Which would you rather have, 2 2x4 bricks or 4 2x2 bricks? Which do you think gives you more freedom? Somebody give me an answer. All right, somebody give me another answer. Okay, somebody give me another answer. They're the same. So the question is, what does your intuition say? Would you rather have a lot of small pieces or fewer big pieces where the big pieces have more ways of combining? Without doing the calculation, there's a way to get some sense of what the answer might be. Any idea how you might get a sense of what the answer might be without doing the calculation? So this leads to the subject of estimation. This is something that's not taught, in my mind, nearly enough in classes. What I like to do is I like to go to extreme cases and consider what would happen in the extremes. How many people have played, like Wii Baseball or anything like that? All right. The special effects are phenomenal. All right. I grew up in the 70s and 80s. The special effects were not quite as good. It was a lot of text-based stuff. And I still remember my brother and his best friend had created players, because you could do that in one of the more advanced games. And they created the pitcher who always struck out every batter and the batter who always hit home runs. The immovable force versus the irresistible, the immovable object versus the irresistible force. And so they had the pitcher who always strikes out everybody face the batter who always hits a home run. What do you think happened? I'm sorry? Almost. There was a noticeable pause for a couple of minutes as the computer was trying to figure out, what the hell do I do? And finally, the computer turned out the only reasonable answer in hindsight. No. Nope. Nope. Not game over. Double. Home run is 4 bases. Strikeout is 0 bases. Split the difference, it's a double. And so, again, the computer found a way to deal with something like this. When you're programming, you want to have, safeties in place so that in situations like this, the game does not crash. Let's go to an extreme case. So the reason I had to use these giant bricks is I actually wanted some extreme cases. Okay? Instead of having a bunch of 2x4s, let's say I have a bunch of 1x1s. How many ways can I combine them? 1, right? Doesn't matter how many I have. If I've got to combine them all, there's only one way to do it. Look at extreme cases. There's a lot you can learn from extreme cases. And so if I go to the ridiculous case of just 1x1s, we can see in a situation like that, it's really bad. There's not that many possibilities. So we expect, if we're breaking things down too much, there's going to be problems. However, as we start getting a little bit bigger, as we now get up to 2x2s, I didn't bring any 2x2s, I have a 3x2. We have a lot more of these. And you start to think about multiplicative things and having a lot of different pieces and multiplying, having more levels. The bigger the pieces, the fewer levels I can get. With 2 bricks like this, I can only do 2 levels. Actually, I have my daughter's rainbow. She won't mind. Well, that's not a given, but if I have something like this, I now have 4 pieces. I have lots of different ways of combining the 4 pieces. And so now, I can do something truly beautiful like this. And I have all the different ways now of sliding things over and combining things. And so my feeling is I'd probably rather have the 4 2x2s than the 2 2x4s. But I don't know enough to just say for sure that that's better. Just that's my gut instinct. At some point, however, I do think having a bunch of small pieces will be more valuable than having a smaller number of larger pieces, just because of the multiplicative process. And you just start to look at extremes. Imagine you now have just 1 piece. You have a 2x8 piece. Well, clearly, I'd rather have a bunch of 2x2s than 1 2x8. There's nothing I can do. So you have some sense of what's going on with the extremes. As an aside, how many of you have taken calculus? Okay. So, again, the point of this is to use Legos as a motivator to interesting mathematics. I will show you the derivative that won the Cold War. Okay. Probably none of you remember the Cold War. I was in high school, and for extra credit, I was doing a debate, is the Cold War over or not? And the night before the debate, I turn on the TV to relax, and they interrupt the broadcast for the fall of the Berlin Wall. It was the easiest debate I've ever had in my life, and probably the only time I ever publicly danced in class. The debate began, in fact, with the other team asking, do we have to go through with this? All right. Are there any econ majors here? Okay. In economics, do you make reasonable or unreasonable assumptions? It's okay, you can say it, we all know. Unreasonable assumptions. So let's do some unreasonable assumptions. All right, we're going to simplify the US and world economy. All right, we will assume that the government only gets revenue by taxing companies. And you can choose the tax rate anywhere from 0 to 100%. It is actually technically possible to tax above 100%. I was actually in a bracket above 100% when you consider reduced financial aid at one point, but we will assume the tax rate is between 0 and 100. How much revenue does the government collect with a 0% tax rate? How much revenue does the government collect with a 0% tax rate? $0. How much revenue does the government collect with a 100% tax rate? $0. I'm not being paid to do this. I'm actually doing this class for fun. This is my year off in teaching winter studies. I love doing this. Most people, however, are not going to work when you pay them nothing. The revenue will be 0. So at a 100% tax rate, you get no revenue. What do you think the revenue curve looks like as a function of tax rate? Goes up and down. So this is called the Laffer curve, and Laffer is spelled with 2 F's, not other ways. This is, to me, intuitively obvious. The difficulty is, where are you on the Laffer curve? Depending on where you are, you can actually raise revenue by lowering taxes. You can also decrease revenue by lowering taxes. You need to figure out where you are. And if you know calculus, that's where the sign of the derivative helps you. If the derivative is positive, then you're increasing. If the derivative is negative, you're decreasing. So trying to figure out where you are is extremely important. It's extremely difficult. Extra credit to anybody who can find a politician talking about stuff like this in any debate and not just simple sound bites. All right? But this is the power of looking at extreme cases. The extreme case of 0% and 100%, these are very clear. And from that, we can fill in roughly what's going on. And we can get some idea of what we should do. And to me, this is the power of mathematics. This is the power of looking at extreme situations and getting a sense of what you should be doing, how you should be handling things. Okay. Any questions about any of the stuff we've seen up till now? Okay, so we've talked about different ways of combining bricks. We've talked about how we want to consider structures either the same or different. This is extremely important, as I said, in biology. I'll post some reading about this in terms of which compounds can kill you versus saving you. The next thing, I'm not going to go through it in class. I'll leave it for links for you to work out, is to measure complexity. So if you look at it, a giant rock probably has more atoms in it than I do. I'd like to believe I am better than a giant rock. That sheer number is not important. Why am I better than a rock? This should not be a hard question. I can talk. Yes. Why am I able to talk and do all these great things?
There are a bunch of different ways that the atoms be arranged for the rock to still be a rock, but there are only a few ways the atoms
Good.
be arranged.
There's a lot of different ways to arrange things. And I have a lot of subroutines, sub-procedures, sub-parts that are actually capable of doing lots of good things. All right, so if nothing else, you've learned your professor is better than a rock. Okay? Sheer number, sheer size does not matter. This is why Yoda is such a badass. Right? When you look at Lego sets, we talked a little bit about what the right metric is. You could look at complexity. There are several ways to measure the complexity of a Lego set. One is, how difficult it is to build. Is that an easy statistic or a hard statistic? That's a little hard. You actually have to start building the damn thing. You have to worry about maybe, are there better ways of doing it? How many of you have ever used knockoff Legos, like Mega Blocks or stuff like that? How many of you have gone all the way down to Best Lock? I know this is being recorded, so I won't say anything about whether or not you should ever buy a Best Lock set. But there are differences in terms of how well the pieces snap together. There's also differences in terms of how the instructions are done. And I was doing a Mega Block set, and it was the Enterprise D, and they had these support pieces that we added far too late in the building process. It would have been very helpful to put them in a lot earlier. Just because they give you the instructions in a certain way does not mean that is the way you should build things. you have a lot of different ways to measure complexity. Building, how difficult it is to build, that's a great way, but that's hard to deal with. Another thing you could do is maybe the kind of fun you can have playing with the set. Again, difficult thing to quantify. This kid seems to be more entertained with this Lego set than that Lego set. When I have to start controlling for different kids and their preferences and whatnot, we want an easy statistic to compare different Lego sets. What's the simplest way you can measure complexity of one Lego set to another? Simplest way. Number of pieces of the set. Okay? This set has more pieces. This set is better. I will get the London Bridge and we'll see how much fun that set is. I think the Superstar Destroyer is a little bit more fun. There's something about walking through the hallways holding a Superstar Destroyer. It's even better to actually be walking with 3 Superstar Destroyers, which we've done, and actually have a fleet. Right now, one of them is at OIT, one of them is at Student Life, and one of them is in my office. We'll have more as the semester progresses. All right, piece count is one way to do it, but maybe not the best, because the London Bridge, beats the Superstar Destroyer by either 25% or 33%, depending on your perspective. What's another way to measure? Yes? The number of different types of pieces. And so one thing you can look at is, as your set becomes bigger, as it has more pieces, how many distinct types of pieces do you have? And you can even go further and say, how many copies of each piece do you have? If I just have one copy of one special piece, maybe I have Elsa's crown. And yes, we have pieces for stuff like that now. I don't know how much credit I want to give the set for having Elsa has a crown, Elsa has a wand. All right, well, maybe that is fun to play with. But it's only one copy of that piece. So maybe you want to have some kind of control of how many types of pieces you have and how many times they occur. So there's a very interesting relationship to look at the number of types of pieces you have as a function of the number of pieces in the set. What kind of relationship do you expect it to have? As I increase the size of the set, what do you expect? You expect to have more types. Do you expect the number of types to be increasing without limit? As your set gets bigger and bigger and bigger, do you expect there to be more and more special types of pieces? Do you expect the rate of increase to be getting smaller? So maybe, I'm hearing something like this. It's growing, but the larger my set is, the fewer new pieces I'm getting. And I'll just get maybe more and more copies of some of the other smaller pieces. And so when you have plots like this, here's x, here's y, what you often do is you do what's called a log-log plot. And you plot the log of x, log of the number of pieces in the set, versus the log of y, the number of distinct pieces. And if you have any nice relationship, any nice power relationship, it becomes linear on a log-log plot. And so here the slope would be less than 1. So maybe it would be something like this on a log-log plot. So log of number of pieces, and here the log of number of distinct. And then it becomes an interesting question to look at how many different distinct pieces do you have? How many copies of them do you have? Situations where something this might be useful is people are trying to talk about how valuable they are as a researcher. And so there's Google Scholar, there's all these different sites that talk about how good you are. What do you think might be a good metric for how good an author is, how good a researcher is? Yes? How many times they get cited by other papers? Now you've got to be very careful with your definition of other papers. What do you mean by other papers? Okay. One of the things I do is if I had to describe myself in one word, it would be opportunity. I love providing opportunities for students. And when I have students taking math classes with me, I actually let them referee for real journals. And I give them papers and I have them decide whether or not the paper should be published. So that the journals don't panic too much, I tell them I will also referee the paper and I will talk with the students and make sure we all come to agreement. And I remember a couple of years ago, 2 of my students came to me with concerns about a paper that they were refereeing. And they were right to have concerns. The paper sucked. And they said, we noticed that there are only 6 references in this paper, and all the references are by the 2 authors of this paper. I said, yes, and what does that tell you? Does anybody else in the world care about this? No. And so when you say, how many citations are there? An interesting thing to look at is, how many people cite the paper other than authors of the paper? And so, there's a great deal of research being done in fields like this to try to measure the impact of someone. How often are the papers? I think Google Scholar, there's something called the H index. Your H value is 5 if you've written 5 papers, each of which have been cited by 5 other papers. Your H index is 8 if you've written 8 papers which have been cited by 8 other papers. And you just use the highest number possible. And this is a great way to see how impactful you are. Different fields have different conventions. Almost surely, there's definitely nuclear physics papers, particle accelerator papers with more authors than the number of people in this room. There's some papers with 200 to 400 authors on it. And so you've got to be very careful about comparing things across field. And this leads to some great questions in statistics as to how do you want to do these comparisons and these metrics. But it all comes down to the very basic questions and the basic mathematics we've been looking at with Legos. How do we measure complexity? How do we measure value? And these are extremely important. When people are trying to go up for tenure, when people are trying to be hired, they're trying to make the case. And so one of the applicants to Williams College was making the case that they have a really high H index and they should be valued highly. And so I then started doing some research into this and looking at, well, yes, but they work in a more applied field, and their number is not so great in the field that they're in. And you always want to put things in context. And it's very easy to mislead. How many of you have taken a stats class? I used to say if you take a stats class, a probability class, and a programming class, you will always have a job. You may not like it, but you will have a job. There was a student at Monroe College who sued her institution because she did not get a job upon graduation, so I have to be a little bit more careful. Now you can actually download her lawsuit because of the Freedom of Information Act, where she misspells the word tuition. And she claims discrimination, that the school does more for people with higher GPAs than lower GPAs, and her 2.6 is just as good as a 3.6. So I cannot promise you a job if you take a stats class, a probability class, and a computer science class, but I will strongly encourage you to do so. It is very easy to manipulate things. So I will do a quick little manipulation right now, and then I'll see, and maybe do 1 or 2 other things, and then we'll call it a day. All right. Any college football fans here? All right. College football is a very tough sport to rank because you have so few interconference games between the conferences. It's really tough to tell how good teams are. There's a lot of great math research done in terms of trying to figure out the right way to rank teams. If anybody is interested in stuff like this, please let me know. Imagine you take your favorite sport and I tell you your team has won 3 wins in last 4 games. And let's say we're midway through the season. What's your team's winning percentage locally? 75%, 750. Is your team playing well? Yeah. How well is the team really playing? It depends a little bit on the team that they play. Well, in fact, something has happened. Let's look at their last 4 games. 1, 2, 3, 4. And let's go back a little bit further in time. Anybody know what happened to this team 5 games ago? They lost. How do you know that? Otherwise, I would have said they have 4 wins in their last 5 games. They had to have lost 5 games ago. Otherwise, I would have said they've got 4 wins in 5. It's all about misleading. Okay? What about 6 games ago? Do we have any information? We don't know what happened 6 games ago. All right, let's look at the last 3 games. Do you know anything about their last 3 games? We know they won game 4. Otherwise, I would have said they've won 3 in a row. So we know they won game 4. So now, in the first 3 games, we have a win, and a loss. An average team, how many wins do you expect in 3 games? 1 or 2. This team is essentially an average team. It looks a little bit better. It's very easy to manipulate and mislead. You want to look at the right statistics. You want to be very careful about the information that's being presented. And so, again, there's lots of different things we can talk about with Legos. To me, I like it as a springboard to looking at the right statistics and trying to figure out complexities of sets. And what is the right number to be looking at. Here, in the last 5 games, they've won 3 and lost 2. Well, you expect to win 2.5 out of 5 games. This is essentially an average team. It looks much better at first, but it's essentially an average team. You always have to be careful about what information you're being given and how it's being presented. When I was an undergraduate at Yale, there was a grade strike by the graduate students, and it didn't really affect me because I was a science major. I was a double geek in math and physics, but the graduate students in the humanities wanted to form a union, and they absconded with the final exams and final papers in a lot of the humanities classes. And they refused to give them up until their demands were met. Now again, for those of us in the sciences, it didn't really matter because the science students were kicked out of all union discussions because they were always voting no. And so because they were losing the vote, they just said, well, let's just kick them out from the discussions. So I was at home, and this made the national news, and they had a reporter down there who was interviewing 2 graduate students from Yale University, asking them for what they thought. And I remember it said, Robin Brown, grad student, Yale University, something similar for the other student, and they asked them for their thoughts. And they sounded perfectly reasonable, and they talked about the views of the graduate students. They never lied, but they also never mentioned that Robin Brown was the president of the striking organization, and the other person was the vice president. It's possible that the reporter was just walking through campus and just happened to run into 2 students, and I could easily see this time of year the president and the vice president would be walking together and discussing things. But nowhere in the story did they mention who they were. I want you to be very aware of what information is given, how is it presented. It is very easy to manipulate perceptions with statistics. And so, to me, this is a really good thing to look at for something like this. All right, the last thing I want to do today is talk a little bit about efficiency and complexity. So we talked a little bit about tic-tac-toe. I'm not going to do too much on Rubik's Cubes, primarily because I have a colleague, Professor Stoichu, who actually teaches a class on this. I finally learned how to do a Rubik's Cube. I'm not fast, but I can at least